Okay, in this video, I'm going to do the activities that follow the 2.5 exercise, the problems 1 to 10 that I've already done. So we're going to go over a couple of examples, and then I'm going to give you an assignment in our notes packet. So this says, in your textbook, read the beginning of section 2.5, looking especially at example 1 and example 2. So I would suggest that you do that. I'm going to go ahead and do this example for you. So you are in your house throwing a ball up in the air in a parabolic fashion, like a parabola, such that its movement can be modeled by this quadratic expression. Find using calculus the CV that will maximize the height of the ball. Okay, so we're going to maximize the height of the ball. Once you have identified the CV, what I want you to do next is to build a sign chart and use it to illustrate a first and second derivative test. Write an explanation of your sign chart telling what the first derivative test indicates using the word slope and what the second derivative indicates using the word concavity. So pretty much what we are used to doing. And then provide a sketch. Okay, if the height of the ceiling, here's our second question. So this is your first assignment, normal. Now, second question, if the height of the ceiling in the room is 20 feet, will you hit the ceiling before you reach the maximum, at the maximum, or never? And how do you know this? Okay, so let's start our problem. So our function is negative 4t squared plus 16t plus 3. Take your first derivative, and you're getting negative 8t plus 16. Take your second derivative, and I'm getting negative 8, which tells me it's always going to be concave down, which you should know just looking at the leading coefficient of negative 4 of your original function. But let's go ahead and get our critical value. It looks to me like it's going to reach a max at the time of 2 seconds, right? If I set that equal to 0. So let's go ahead and do our little sign chart. Here's 2. Okay, let's check to the right, to the left and right of 2. If I plug in a 0, I'm getting a positive. If I plug in a 3 in the first derivative, I'm getting a negative. I already know that the second derivative is going to be negative. So what do I have? I have this kind of shape. So here's our statements. Okay, so I'm going to say at CV equals 2, the slope changes from positive to negative, which gives me a max. Okay, so I use the word slope. And then I can say that f prime prime of 2 is less than 0. So therefore, that gives me concave down. So here I've used the word concavity. And that leads to a max. Okay, so I have sign chart and I have my statement. So can I give myself a little picture? Let's see, because I haven't figured out what the height is going to be yet. So I'm going to plug the 2 into the original equation. So what I find is f of 2 is going to be, do a little math, and it's going to be 19 feet. So in terms of a little sketch of my function, what I know is that it starts out at 3. Whoops. Right here is going to be 3. It's going to go up and down, and here's the max is 2, and that's going to be 19. So anyway, I have a little sketch. So that's all good. Okay, so I think I've done everything in step A. So now, if the height of the ceiling in the room is 20 feet, will you hit the ceiling? So you're never going to hit the ceiling, right? Because 19 is the highest you ever get to. So the answer is no. The max height, so let me back up a little bit. The max height of ball is 19 feet, and therefore you do not hit a 20-foot ceiling. Okay, so that was a pretty practical example of a maximization. Okay, in the next page, we're going to go through another example, and this is going to be a different kind of problem, but it's going to be the same thing in terms of being practical as opposed to just number problems. Okay, so let me go to the next page, and I'll load that up for us. Okay, so here again, I'm having you go into your textbook, which is never a bad idea, and I'm having you look at examples. So I'm going to set up this problem, but I would advise that you go ahead back and look at your textbook and, kind of see the examples because it'll help you with your understanding. But for this problem, it says, given 80 feet of fencing, find the maximization of the area of your garden when you use your house for one side. So that means that the fencing is only going to be on 3 sides. So here's your house. Here's the garden. And what I want you to notice is that you have no equation. So you have to build your own equation. So they want to find the maximum area. So if you say that, let's say that these are your y's, this is your x, okay? They told me that I'm going to use fencing, and I have 80 feet of fencing. So therefore, what I can say is that my constraint is that, according to these variables, the way I set it up, 2y plus x has to equal 80. Okay, I want to use up all my fencing. And my optimization is going to be to maximize the area, and I know that area is length times width, and in this case it would be x times y. Okay, so my area, so let me call that area, is x times y. Once more, I can't do this problem until I get it into only one variable. So since I know that 2y plus x equals 80, why don't I solve this in terms of y? So I will say that my area equals, x is going to be what? 80 minus 2y. So 80 minus 2y times y. And you see how I use the constraint to get rid of one of my terms. So now I have everything in terms of y, so that's good. I'm going to go ahead and multiply this out. So this is 80y minus 2y squared. Take your first derivative, and you're getting 80 minus 4y. Okay, I'm going to take my second derivative, and I'm going to get negative 4. Now that's going to tell me that the value I get from my critical value will indeed maximize because a prime prime is always negative. So get your critical value now, and if I set that equal to 0, I'm going to find that y equals 20. Okay, so do your little critical value chart. So here's my 20. If I were to check on either side, if I plug a 0 in, it's going to be positive. If I put a 30 in, for example, it's going to be negative. I know that my second derivative is already negative, so therefore I know that my shape is going to be a maximization, so that's all good. Okay, so I should write a statement. So to write a statement, I'm going to say at CV of 20, the slope changes positive to negative, which means I have a max. And then I can say that a prime prime of anything really, but I'll put my 20 in here, is going to always be less than 0, which means it is concave down, which also gives me a max. So that's all good. Okay, so let's see what we have here. I need to figure out what is the maximum area. I want to figure out my x and y. So far I know that y is 20, and since 2 times 20 plus x equals 80, then this is 40 plus x equals 80. So that means x has to be 40. So these are feet. And then what is the maximum area? So 20 times 40 is 800, and this would be square feet. So this is a rectangle, and the dimensions are 20 by 40. All right, so that's our answer. Now, the next problem is kind of interesting. The next problem we're going to do doesn't constrain you to use your house as a wall. It allows you to have any shape you want for your garden. Okay, so we have the same fencing, but the question is, what will our shape look like then? So let's do that on the next page. Okay, so here's our setup. We still have 80 feet of fencing. So what I know now is that 2x plus 2y has to be 80. If I divide everything by 2, I get x plus y has to be 40. So let me solve for y this time. So y is going to be 40 minus x. So let's go ahead and try to maximize the area again. So I have y is 40 minus x. So x times 40 minus x. So let's multiply that out. So 40x minus x squared. And then a prime is going to be 40 minus 2x. And a prime prime is going to be minus 2, which is negative, which is good. So in this case, I'm going to find that x equals 20. And since x plus y is 40, that also tells me that y equals 20. So look what's going on. If I don't have to use the side of the house, the maximized area ends up being a square. If I use the side of the house, the maximum area, or the maximizing shape ends up being a rectangle. So I thought that was kind of interesting. So let's finish our problem by doing our sign chart. So that's my x. This time I found the x. And in terms of my slope, if I plug in a 0, it's positive. If I plug in a 30, it's going to be negative. I already know this is negative, and that means my shape is like this, and I'm done. So the maximum area now is going to be area equals 20 times 20, which is going to be 400 feet squared. So another thing that's interesting is my area is less this way. I have the same fencing, but because I had to fence all 4 sides, I have a smaller area than I did when I had the rectangle and only had to fence 3 sides. So I'm going to leave the statement to you this time, but this should give you a good handle on this material.